Hi everyone, my name is Eugene. I'm the software developer at CoreOS and maintainer of Flannel, and I'm here with Rajat from Red Hat. And we're here to talk to you about Flannel, what it is, and then the upcoming changes that we have planned for it. Okay, so what is Flannel? Why did we build it? Well, we want to be able to run containers. We want to be able to run multiple containers on the same host. But if these containers are all running web apps, then it's very easy for them to conflict on ports if they are sharing the same networking stack with the host. So they can easily conflict on port 80 or port 8000, wherever they are running on. So we can fix that by giving each container its own network stack, and then they're going to get their own IP. However, if that IP is only good for on that host, if it's only known on that host, then for any traffic that's coming from outside of the host, we still have to port map the container ports over to the host ports. And then we are back to the same problem with conflicts, and we haven't actually solved anything. In fact, we've made things worse because now we have hidden the true IP and port of the container from the application. So this is kind of the usual net problem that I'm sure many of you are familiar with. So what we actually want is we want to give every container an IP, but we want that IP to be as globally routable as possible. And even if we can't get it truly globally routable, having it routable within a cluster, within a data center, is actually good enough for majority of cases. So this is what Flannel tries to help you out with and make that a reality. So let's see how Flannel works. So here we have etcd, that's the thing in the center. And we use it for both the storage and the coordination of all the Flannel nodes. So here we have configured a Flannel network to be a 10.1/16. And then every worker node is going to draw from this overall Flannel network a /24. So here we have 4 hosts, and each one has been allocated a /24 out of the bigger network. So then, once we have a /24 assigned to each host, the container runtime, such as Docker or Rocket, will assign an individual IP out of that /24 subnet. So here we have 2 hosts and 2 containers, the .58 and .37, and the .8 wants to send an IP packet to .7. So there's this IP packet blowing up, and in this case we are using encapsulation, and we'll talk more about other ways of getting this accomplished. But here we're using encapsulation. You can see that the inner packet, that's the packet that the container has decided to send, is being wrapped inside another IP packet, actually inside a UDP packet. And then the wrapped packet, the encapsulated packet, gets sent over the existing infrastructure and then gets unwrapped at the receiving end and forwarded over to the destination container. So now let's take a look a little bit more detail about how that subnet allocation happens for each host. So here we already have a etcd, and we see that 2 hosts, A and B, have been allocated a .23 and .45. And now host C wants to come in and allocate itself a /24 as well. So the first thing it does is it issues a get to etcd, and it just lists or gets all of the allocated subnets in the cluster. Once it has that list, it picks a random unallocated available subnet and does an atomic commit. So here it picked a .67, and it tries to do an etcd cuddle set, basically, just tries to set a value to claim it for itself. If it succeeds, then it gets added to the list stored in etcd, and everything is well. However, you can, in an unlucky case where another host, host D, tries to do the exact same thing at exactly the same time, it's going to fail because the commits are atomic, that put is atomic. So if it happens to run into this case where it fails, what it's going to do is just going to retry. So we're using optimistic concurrency here. Finally, once it has successfully allocated itself a subnet, it places a watch, which is actually implemented as HTTP long polling, But it places a watch on that CoreOS.com network subnets directory, and it then gets notified of any changes to that directory. So it's going to see any changes to the cluster membership, any additions or deletions. And so it's going to be able to keep its mapping as extremely current. There's milliseconds of latency. Okay, so that's how the subnet allocation works, but now we actually have to do the forwarding plane. We have to forward the packets from one host to the other. And we have a variety of techniques to do that. We are calling them backends. So the first two techniques use encapsulation. This is kind of what I talked about in the previous, in the slides, few slides back. And we have two types of encapsulation. One is IP and UDP. It's done in user space. It uses a TON device, a very proven technology, very old, but it is a little bit slow. And then we can also use VXLAN, which is a new, fairly new protocol for encapsulating Ethernet packets also in UDP. And this can be done completely in the kernel. In this case, flannel just does the manipulation of the in-kernel data structures and acts as a control plane. We also have two backends that have been graciously contributed by the community, and I'm calling them manipulation backends. So instead of encapsulating the packets, what they do is they manipulate different routing tables. So the first one, the AWS VPC, it basically manipulates the VPC router to say that this subnet is actually being backed by this instance. And the host gateway is similar, but it manipulates the routes on the host. It only works within one subnet, but it basically makes the host Ethernet adapter, the host IP, be the next hub. So it's very, very simple, but it only works on one subnet. Okay, so that's kind of the overview of Flannel. And now I want to talk a little bit about the roadmap and where we are going next. So the first thing is multi-network support. So it's actually possible to do multi-networks today. All you have to do is run multiple instances of Flannel daemon and just prefix it with, or give it the --etcd prefix, which is and point it to different directories in etcd, and then they're not going to conflict. However, we've received multiple requests to make this more user-friendly, so we want to make it a first-class citizen within Flannel, and it's basically going to be the same thing, except you're only going to need to run one Flannel daemon. So we're still going to namespace the different tenants of different networks using etcd directories, and then on the back end we have to use something like different ports or VNIDs depending on the back end to segregate the traffic. Next up is Flannel Cuddle. So on the admin, if anyone has used Flannel, they probably have noticed that on the admin side, it's actually not very user-friendly right now. We don't have a control utility. And the only thing we have is basically etcd cuddle, and you can just directly introspect what's in etcd to get the status. So if you need to push the config in, you end up putting JSON documents into etcd. So we want to make it a little bit more user-friendly by creating a utility for both configuration and introspection. Next up, client-server option. So it's actually, I think, a great feature that Flannel is masterless or serverless. There is no central point of failure. The only thing that they rely on is etcd, but etcd is distributed and fault-tolerant, so it's not really a problem. However, for some deployments, it is actually beneficial to run a server to front the etcd. This allows only the server to have access to etcd, and then all the worker nodes then don't get access. It's very important from a security standpoint. So we are still going to do the server in a stateless fashion. So all the data is still going to be stored in etcd. So if the server fails for some reason, it can be easily failed over to another instance. It also yields us a possibility of doing certain backend manipulation manipulations purely on the server. So for example, in the AWS VPC backend that I talked about, when it manipulates the the VPC routing entries, that operation is privileged and you need a security token to do the manipulation. Right now, the token needs to be present on all the worker nodes, which is not ideal from a security standpoint. If you have a server in place, then we can put the token just on the server, and then the nodes don't have to have that information. And with that, I'd like to turn it over to Rajat, who's going to talk a little bit more about multi-net.
Hey, so I want to touch upon this topic. This is multiple networks or tenants on a single deployment of Flannel. There was an earlier talk today of average Joe from QE landing up on production. And one of the things that we mentioned, hey, let's secure the network. Why should QE or test environment have access to the same nodes or same containers? Now we're not talking about nodes here, we're talking about containers. So, and down button, okay, this one. Now this diagram explains how, or why rather, we would possibly need separate networks for each tenant. Now I mean separate networks, and I correlate at least for this talk about that they're correlated to one tenant. And I got two hosts here, container 1 and container 3 are odd guys. They're birds of the same feather. They want to talk to each other. They do not want to cross-talk on the even network. And they could be different customers. It could be Coke and Pepsi. They don't want to oversee their traffic. It could be test or prod. They could be two departments, finance or HR, or two big companies on a platform. I don't know, Google or NSA. Maybe not. Or yeah, Coke and Pepsi. That's good. So, so how do you get this going? And there's one way of having different Flannel daemons running on each host, but possibly we want to get it done easily. And then when this stuff is running, we do not want to bother the users with saying, hey, what was inside, or what's going on? How did you separate? This is a feature, and it will come out of the box. You define yourself as a tenant, and the administrator says, okay, you get a new network. This is not how it was supposed to pan out, but anyway. So Flannel admin says, hey, customer 1, please choose your L3 subnet. L3 means IP address. So he says, hey, I want 10, 20, 30, and I want 256 containers out of that. Can you please assign IP addresses out of this? And the admin says, okay, no problem. And customer 2 says, I want that too. And well, how do you get that done? So this is some feature that we want to get done. This is part of the roadmap of Flannel, and we want to get that across, that we should be able to have overlapping IP addresses from different tenants be supported. Now, what are the use cases? Why would a customer want it? Why can't the admin go back and say, hey, customer 1, no, you don't get this because someone else got that. That may not be entirely possible if you're hosting a PaaS, which is online, and say, hey, no. So Amazon comes back and says, VPC, you don't get to choose your L3. No, that is not going to fly, right? So same thing in the container world when you're hosting a PaaS for containers. This is a likely feature that you would want to have, and Flannel intends to support it. Another use case, which I don't have a good slide for and about, is when, let's say, you've got department 1 inside your company, and you're using Kubernetes or OpenShift or something, or and this is a container network, and you want to say, hey, I want to do some cloud burst, and I want to go out and have my containers use the same IP addresses, same IP address range that I'm already using for my inside stuff. And then you say, okay, why do you want to do that? Because I want to have my firewall rules saying anything which belongs to 10, 20, 30 X is good, anything outside, drop. That's my firewall rule. And if I ended up saying that, yes, you can have a cloud burst, but in a cloud, you're going to have some random IP addresses. The first one is good enough for your firewall, but the second one or the second set is going to have some 11, 12, 13 rule. Then you say, okay, I go back and change my IP tables rules and stuff. That's not going to work. So for that reason also, you may want multiple networks with overlapping IP addresses. This is a diagram. Now, container 1 said, I got 10, 20, 30, 41. I want to reach 10, 20, 30, 42, which is lying on host B. Flannel will figure that out, how to send that across. When it lands on host B, and it says, oh, I got 2 IP addresses, which is the same destination. Now I got to figure out what they mean and then where the packet needs to be eventually delivered. So it says, okay, I will figure it out by using a tuple of network ID, IP address, or MAC address. As long as these 3 are unique, I can uniquely identify the destination wherever it may be inside this flannel network, while the hosts may be in your place or in the cloud, burst or not, or wherever the range is. So as long as host A is reachable to reach host B, Flannel figures that out. How? We want to use OpenVSwitch. Why OVS? There's this link. It has got a 400-word good, nice essay about why. But the beauty points are, we want to use OpenFlow to manage the rules around the tuple. Well, this is network ID, IP address. MAC address may not always be needed. We could have just layer 3 switching. There's a little more details there, but OVS has good support there. And there is rally around hardware support. There was a talk in the morning, Intel doing some hardware stuff to accelerate and offload some stuff. I know OVS suits better there. They're working on that, and they already have something DP stuff, everything, which is VXLAN offload and everything. There's cross-platform uniformity. Linux kernel, Linux bridge is used today, but that's good enough whenever it's Linux. But if you have an abstraction above this, which OpenVSwitch allows us, that's nicer. And of course, it has a wide range of encapsulation protocols, VXLAN, NVGRE, and whatnot. Whatever the new famous shiny kid on the block, I guess OpenVSwitch would want to support that. These are good points. Why I at least got involved in it initially. OpenVSwitch is open. Yeah, it's certainly popular, and it works. That's why we use it. Final slide. I just had 5 slides, except the 6th one. Yeah, this is the one. Yeah, so OVS has a flannel backend. Now, how do we use this client-server architecture, which Eugene just talked about? We want to use the client-server architecture. Now, what we would do is probably have all the hosts say, I want an L3 subnet for tenant A. So give me a lease there. Now, earlier, it used to say, give me a subnet, and it would get the entire subnet. And no matter what container from whichever tenant or customer would land, it would get the container IP address from the subnet that it got. But now we could possibly get pre-allocated L3 subnets per tenant on a host, and then the flannel daemon would accordingly say, this junk that is written here is some sort of OpenFlow rules saying, oh, well, if the tunnel ID is 10, which is customer 10, and the destination is this MAC address, go to this port and stuff like that, which OpenVSwitch is apparently good at handling. The result being that we would be able to have multiple networks, which will support multiple tenants, which will be isolated as a primary case, and possibly have quality of service rules as an advanced case. Thank you. If you guys have questions, then yes. Sorry, he was first.
So, do you have any plans around being able to run a flannel network over an untrusted network? Transporting flannel back.
Eugene has some answer, but the question is that do you plan to run flannel and do networking over an untrusted network? I don't know if Eugene has an answer, but I can say my words then.
Okay, it's not on the roadmap as of right now, but it is a use case that keeps coming up. I will say that it should be possible today to set up IPsec on top of a flannel network to get done. It's just flannel doesn't actually do the setup. Would it be nice to get that working? Yeah, but I think that we often want to run. I think customers often want to run flannel over untrusted networks between different data centers. The problem is that running flannel between data centers, there are some other gotchas that you have to also overcome. For example, you have to span that CD cluster over multiple data centers, which in itself is sometimes tricky. So I think at some point we will address kind of this wider theme of running flannel across multiple data centers, but it is not, at least on my roadmap right now, but PRs are always welcome.
Oh, well, I think that was good enough, I guess. I have no more words, yeah.
Is there a loss of reliability, even theoretical, by dropping from TCP to UDP?
So the encapsulation is kind of a UDP thing, but the layer above that, your own protocol which you use to transmit, if it's TCP, then you take care of it. And by itself, it's based on UDP, the encapsulation. The new stuff that we eventually might have is just going to be pure network. It doesn't even bother, for example, IPv LAN. But if you end up using UDP in your application, yes, they'll be dropped.
And a follow-up to that is, do you do anything in particular with UDP for congestion control? Like, what's it called? Tsunami or something like that?
Yeah, so the question is that do we do anything with congestion control on the flannel network? The answer is no, as of today. There is some scope, at least, with having some quality of service, I was just mentioning by the last slide, that we could have, but I guess that's a little way out. First, we should have multi-tenancy, and then we should possibly have, once we have these programmable SDN, then we can probably introduce some QoS terms there, saying not only isolate, but limit it. Performance penalty on what? The encapsulation is kind of well known, well documented. We internally have at Red Hat done some experiments, and yes, there is performance penalty if you use VXLAN, but there is hardware offload available out of the box. No, you have to configure a lot of stuff, but no, nothing out of the box. It's a little difficult, but so with hardware offload, I think we get close to acceptable. Without it, the advantage is that it would work anywhere, but yes, there is performance penalty.
I actually tried to measure the performance penalties, especially with VXLAN, and I have to say that it's actually has been quite tricky to do because when you're running in cloud environments, the network has so much variability that it was actually difficult to measure the true penalty because the variance was on the order of magnitude of the mean, and it was actually without the flannel coming into the picture. So there's definitely overhead. VXLAN takes 50 bytes overhead, but I don't actually have the true numbers on what the overhead is because I was never able to accurately measure it.
Yes.
So, given the challenges you've had around uniquely identifying IPs, like having duplicate IPs, like why, I guess, did you consider it, and why didn't you go with an IPv6 only, implementation?
Yeah, so the question is, we could have overlapping IPv4 addresses and everything, and there are challenges, and there's work being done, and everything is a lot of hassle. Why don't we just move to IPv6? The answer lies with the applications. If they start using IPv6, they'll push. I was just talking in the morning. I'm saying, why not IPv6? Well, everyone is talking about it, but no one is just doing it, I guess. So we would do it. We would move it entirely to IPv6, and no one would write IPv4 solutions or this thing as soon as applications say, hey, no more IPv4, IPv6. That's a layman's answer, probably. But I don't know if that's sufficient. So yes, IPv6 is a solution, and I think in the next challenge we want to solve is one of the IPv6 support. Right, Eugene?
Yeah.
Yep.
Just want to also say that we have office hours tomorrow from 1:40 p.m. to 10. So if you have any more in-depth questions, feel free to come to the office hours.